Okay, so now let's talk about what cardiovascular functioning actually means when we talk about autonomic nervous system function in a real life perspective. When we measure heart activity, we tend to use something called an ECG or an electrocardiogram. So we could see that picture right here on the side where it's probably something that everyone's seen in different TV shows and all that. But essentially, it's a rhythm that's produced by the electrical activity of your heart. Um, and what's important to note here is that when your heart, it tends to contract and pump in order to try and get blood out of it and into the body, right? In order to make sure that all your organs and other areas that need blood and nutrients are fed the right amount. So, in order to try and contract, it has to produce a very strong electrical signal, and that electrical signal causes it to contract and squeeze. And when it does that, we could see a giant spike that occurs on this ECG waveform. So that is our QRS complex. And if we look at this figure, what we could do is measure the distance between one QRS complex, or the peak of it, which is the R peak, to the next R peak. So when we measure it from one R peak to the next, that time difference between those two is what we use to determine heart rate. So the longer the distance between one R peak to the next, the lower your heart rate is, because that's the amount of time it takes in order to beat. Now, when we say somebody has, for example, a 60 beat per minute heart rate, it's important to consider that that doesn't mean that within that minute, every single beat is at 60. Really, what that means is if you average out, every single beat within within that minute, it'll give you a heart rate of 60. So for somebody who has a 60 heart rate, at one point it could be 40, at another point it could be 70, another point it could be 50, but there's a lot of variation from beat to beat. That variation is actually called heart rate variability, and it's a good proxy or a good indicator of your cardiovascular autonomic nervous system functioning. Generally speaking, a higher heart rate variability tends to reflect a state that's not, riddled with autonomic dysfunction. So, a higher heart rate variability is expected prior to any kind of concussion. And if you take a hit to the head and you get concussed, we tend to see a consistent decrease in heart rate variability. That decreased heart rate variability almost reflects a more stressed state, but there's a lot of nuances that still go into this. For example, if you inhale and then you exhale, your heart rhythm goes up and down as well as you inhale and exhale. If we take a look at this chart here, we see this value SDNN, and even something as simple as that, the standard deviation of your R to R peaks, that tends to decrease when you're concussed. And it's a very, very basic measure, very basic example, but it gives some really strong insights as to, is your body more or less stressed? If you wear these Apple Watches or Fitbits, all of them now give an indication of heart rate variability as well. If you take your heart rate variability recording every morning, you tend to get a good indication of how stressed your system actually is. So aside from heart rate variability, there's also blood pressure and blood pressure responses that tend to get altered when you're concussed. One thing to note is, every time your heart beats, it produces that blood pressure as well, right? So if you consider blood pressure, it's got two values, asystolic and diastolic pressure. And that's usually where we see that 120/80 mark being a healthy number. But what nobody really considers is that variation from beat to beat blood pressure. So every time your heart beats, what's the pressure that it's producing, and how does that vary over time as well? We can look at that beat to beat variability, and that's called blood pressure variability. And that's another really big measure that we see completely altered when somebody's concussed. You see a large decrease in blood pressure variability when somebody takes a hit to the head. And similar to heart rate variability, it provides insights as to that cardiovascular autonomic dysfunction. So blood pressure variability tends to decrease, heart rate variability tends to decrease, and together this reflects a physiological stress, or whole body stress, after a hit to the head. If you consider the relationship between increases and decreases in heart rate and how these correlate, or how these change in response to increases or decreases in blood pressure, you tend to get something called baroreflex sensitivity. This is a coherence measure. You're trying to see, okay, if I have an increase in heart rate, is there a similar increase in blood pressure variability over a certain number of beats? And even blood baroreflex sensitivity, which is a surrogate measure of those changes in heart rate and blood pressure, this tends to be completely altered as well when somebody takes a hit to the head. We tend to see actually an increase in the sensitivity, especially when you get somebody to control their breathing rate and really exaggerate this response. And it's almost like a compensatory response. Your body is overcompensating in order to try and bring it back to some kind of normalcy. And it could be that baroreflex sensitivity increases so much because HRV and blood pressure variability tend to decrease substantially. We've been able to show a lot of these responses in our lab after somebody takes a hit to the head, but there's still quite a bit more work that has to be done in order to develop an exact mechanism. And, one way is if we move away from just looking at HRV and blood pressure variability, but start to look at more about how is the heart actually functioning. And we'll discuss that in just a little bit here. Okay, so we've spoken about the general assessments of heart rate variability and blood pressure variability, basic measures of autonomic nervous system. But one really intriguing assessment now that we're starting to introduce takes a look at cardiac cycle timing intervals. So every time your heart beats, from that beat to the next, there's so many little activities that occur in your heart in order to allow that heartbeat to actually get produced. There's different valves in your heart, there's different flows and passages that the blood has to move through to pick up oxygen. There's different electrical activities that have to occur in order to allow blood to pump at a strong enough degree that it actually pushes through and goes through your entire body. And if we take a look at the different intervals that occur within every single heartbeat, we can call these cardiac cycle timing intervals. And these intervals, again, are really important because now we get some insight as to, okay, what's actually occurring with the heart that's causing these decreases in HRV or BPV or whatever symptom that the patient tends to show after something like a concussion. Now, let's go through, the way that the heart actually allows blood to flow through and produces pressure. So, once you get something called a mitral valve closure, so that's this valve right over here, the valve between the left atrium and the left ventricle, there's so much blood that's been pulled into the left ventricle that it starts to, along with the electrical rhythm, it starts to increase pressure, and with more and more pressure increases, and we can see that with this blue line right here, there tends to be such a strong response that occurs that the aortic valve, or the valve between the ventricle and the aorta, tends to pop open because of the amount of pressure that's produced in the left ventricle. As this valve opens, blood goes from that left ventricle into the aorta and then into the rest of the body. Now, by producing a heart response or a heartbeat, you're actually creating vibrations that we can measure right on your sternum. So we have a little device in our lab. It's called a seismocardiogram. And by placing this device right on the sternum, we're able to measure the vibrations that each heartbeat produces. And from there, we can understand when the valves of the heart open and close. So we can actually tell how long is it taking for the heart to squeeze in order to get all the blood out. How long is the heart relaxing for in order to allow it to get filled with blood. And based on these different timing intervals, we get insights as to what's actually occurring when somebody takes a hit to the head. There's also timing periods where all the valves are closed, and you're getting changes in pressure, so there's no changes in volume, and that's called isovolumic times. These are meant to build up pressure in order to allow the propagation of the next event to occur. And even these timing intervals tend to be altered during some kind of hit to the head. Okay, so now if we go back to concussion, there's a study that we did a couple years ago when I was, again, still in graduate school, and we took that device we were just talking about and placed it on individuals after they got a concussion. And what we were able to show is that when somebody gets a concussion, the amount of time that their heart squeezes for in order to get blood out is drastically reduced compared to when they're at a healthy state. So your heart or your ventricle is under a ton of stress, and what happens is the amount of stress causes that twisting of the heart or contraction of the heart to occur at a much smaller time period than before, when the individual was healthy. And it's not only in the left ventricle this occurs, but in the left atrium as well. We tend to see a large increase in the strength of contraction of the atrium. And again, this represents a systolic problem, both with the atrium and with the left ventricle, after somebody takes a hit to the head. There's also something called a myocardial performance index, or a TI index, that we can derive from the left atrium, and again, similar to the ejection time and the contractile properties of the atrium, there tends to be some dysfunction with this performance index as well. So all in all, these different intervals allow us to understand why there's so much stress under the heart, and essentially it tells us that, hey, after this individual has taken a hit to the head, whether it's a direct or indirect insult to the brain, the dysfunction that occurs at the heart occurs in a variety of different areas and a variety of different patterns.